Write one question. In NO2 minus, oxides of nitrogen structure of different oxides of nitrogen is cut from your syllabus. NO2 minus. In NO2 minus, NO bond length. NO bond length is smaller than the NO bond length NO3 minus. In NO3 minus, NO2 minus, NO bond length that is smaller than this NO bond length of NO3 minus. In NO2 minus, NO minus, or this bond can come NO minus. Now, in this case, this double bond is resonating between this and this, means two bonds. Double bond is resonating with two bonds. But here, in NO3 minus, the double bond is resonating between three bonds. The double bond is resonating between three bonds. Maybe here double bond, or here double bond, or here double bond. Here there is more attraction. Here there is more attraction. More attraction means the double bond is resonating between only two bonds, two NO bonds. So here attraction means smaller bond length, lesser bond length. Next is oxides of phosphorus. Oxides of phosphorus. The main oxides are E is the element. Then generally we can say P2O3 and P2O5. That is P2O3 and P2O5. But they are existing as like P4O6, P4O6 and P4O2. P4O2. Higher oxidation state is acidic as compared to the lower one. Higher oxidation state of phosphorus, that is acidic. Next we are moving to the anomalous properties of nitrogen. Anomalous properties of nitrogen is due to small size and high electronegativity, high ionization enthalpy. These are the reasons for the anomalous properties that we already know. So what are the anomalous properties of nitrogen as compared to this other phosphorus, arsenic, and what are the anomalous properties? Nitrogen. Nitrogen is a gas. Nitrogen is a gas, while others are solids. The compound of nitrogen, that is hydride of nitrogen, NS3. NS3 has got hydrogen bond, H bond, but others hydroids, no H bond. Halides. Halides in the case of nitrogen, only N is stable, but in here only NF3. Only NF3 is stable. We know that it is an exothermic compound, but here all halides are stable. All halides are stable. Then molecular nitrogen is in the form of N2, while in others it is P4, S4. This is due to the catenation here as B4, BI4, SI4. The molecular nitrogen is N2. Next, no covalency of fire. No covalency of fire. But here they can have equivalency of 5 using their d orbitals. Next, R3n double bond O is not possible. Not possible. But here R3P double bond O, R3P double bond O is possible. All these things we have seen. Next, nitrogen can form only P by bonds, but others can form B by bonds, by bonds, and B by bonds. Why? Because nitrogen does not have d orbitals. These are the anomalous properties of nitrogen. P5 bond is not formed by this because on bigger molecule P5 bonds are diffused. It's not stable. Next, dinitrogen N. Dinitrogen. N2 is prepared by the decomposition of sodium acid. Na N3. This is sodium acid on heating gives Na and 3 and 3 2 on heating. This is sodium acid. Sodium acid in this form. This is minus, so this is so sodium acid. Another method of preparation is from NaNO2. NaNO2 plus N4C. We can get nitrogen. Nitrogen NaCl plus N2 NaCl plus H2. So these are the methods of preparation of nitrogen. Nitrogen we know N triple bond N. There is a triple bond means very strong force of attraction between two nitrogens with a triple bond. To break this bond, triple bond, 946 kilojoules of energy is required. That means it is not easy to break this N triple bond N. That means nitrogen N2 is highly unreactive. N2 is highly unreactive. Why? Because we cannot break that triple bond normally. But under drastic condition, means if you give that much condition, the nitrogen can react with metals. For example, lithium. Lithium combines with nitrogen to form lithium nitride. Magnesium forms magnesium nitride. Then nitrogen can combine with hydrogen to form ammonia, and nitrogen can combine with oxygen to form NO. These all things are under drastic conditions. Now we are moving to the compound, famous compound ammonia NH3. Ammonia is manufactured by Haber process. N2 plus 3H2 gives 2NH3. N2 plus 3H2 gives 2NH3. Now this is the equilibrium equation. How to increase the amount of ammonia? According to Lee-Shapier's principle, change the pressure, concentration, or temperature. If you change the pressure, temperature, or concentration of the system in equilibrium, the system will adjust itself to nullify the effect of change. So, if you are increasing the pressure, the system will try to decrease the pressure. If you increase the temperature, the system will absorb that temperature and shows no effect. If you increase the concentration, the system will adjust. It may either move to the forward direction or move to the backward direction. So here, one mole, you can say that it's a number of moles. One mole of nitrogen combines 3 moles of hydrogen. That means all together 4 moles, and here only 2 moles. You know that higher number of particles, higher pressure, lower number of particles, lower pressure. If you increase the pressure, then what will happen? The system will move to decrease the pressure. To decrease the pressure, system will move to where the number of moles are less. That means to the forward direction. So more and more ammonia will be produced. This is an exothermic reaction. 90.4 kilojoules per mole. Increasing the temperature means that heat will be absorbed by ammonia and backward reaction will be proceeded. So, higher temperature is not favorable. Still, to gain that activation energy for the molecules to collide, you have to heat little bit. So, higher pressure, lower temperature, and consumption, of course, the consumption of reactants will give more amount of the product that is ammonia. So normally, a temperature of 700 Kelvin and atmosphere pressure 200 atmosphere and catalyst is used because this N2 and H2 are gases. These are to be adsorbed on a surface. So iron is used as a catalyst. Exactly, iron oxide. Iron oxide as catalyst with a small amount of K2O and Al2O3. These are the conditions favorable for the preparation of ammonia. Means 200 atmospheric pressure, 700 Kelvin, then Fe2O3 as the catalyst with small amount of promoters, that is K2O and Al2O3. Ammonia nitrogen from here and nitrogen from other parts will be coming. They will be mixed. So these nitrogen and hydrogen will be mixed and they are made to pass through high pressure. Means here high pressure of 200 atmospheric pressure. 200 atmospheric pressure will be given and a highly pressurized gas will be going and it is passed through this catalyst, that is Fe2O3 and Al2O3, Fe2O3 and Al2O3 plus T2, and after that the remaining thing is now the ammonia is coming, that is liquefied, and we are getting that. So here, liquid ammonia is obtained. And if there is any N2 and H2 under it, that will be taken. That will be This is unreactive. Unreactive nitrogen and hydrogen. Unreactive nitrogen and hydrogen. Unreactive nitrogen and hydrogen are reverted back again this situation and again there will be passing through this. So this is the chemical process for the preparation of ammonia. Now what are the properties of ammonia? Ammonia, it is soluble in water, soluble in water, H2 to form ammonium hydroxide. So what you are going to get is NH4. And NH4 is a very useful reagent in analysis of salts. In third group of analysis, we use this NH4OH. Fourth group, we use NH4OH. Fifth group, we use NH4OH. So, what is the function in third group? Third group, for Fe3, Fe2 plus and Fe3 plus, to detect this, detect the presence of Fe2 plus or Fe3 plus, we use this ammonium hydroxide. So Fe2 plus plus, for example, FeCl3 plus NH4OH. FeCl3 plus NH4OH will give a brown precipitate, that is Fe2O3 dot XH2. It is a brown precipitate. Now, in fourth group, for example, zinc sulfate, for the identification of 7 plus zinc sulfate plus NH4OH is zinc hydroxide, ZnOH. It's a dirty white crystal. Plus NH4SO2. NH4 twice SO4. So that is the property of ammonium hydroxide. For analysis, we use this ammonium hydroxide. Next, the property of ammonia is a base, you know. Ammonia is a ligand that we learned in coordination compounds. Ammonia can donate a pair of electrons. It is a unit-ended ligand. It is a unit-ended ligand. So it can coordinate with transition metals. For example, Cu, NH3, 2 times 2 plus. This is a deep blue. This is a deep blue substance. The ammonia is coordinating to Cu2 plus. Cu2 plus with 4 Ns. And write Cu2 plus 4 Ns3. You are getting this. If it is silver, Ag plus Ms3. You know that tolerance reagent. Tolerance reagent that is Ag, Ms3 twice tolerance reagent. This is again a coordination complex. Next compound of nitrogen is nitric acid, HNO. Preparation of HNO3. Preparation of HNO3. First, you prepare NO. Then convert that NO to NO2. Then add water to form HNO3. This is the method. Or directly, if you take NaNO3 and H2SO4, Na plus H2SO4, H2SO4, you will get HNO3, HNO3 plus Na plus NaHSO4. Or what I said, prepare NO, prepare NO. Then NO is to be reacted with oxygen to form NO2 you mix with water. So first method is preparation of NO by post-wash process. Post-wash process is starting with NS3 and 4 NS3 and 5 with 4, 5, 4, 6, 4, 6, 6 H2. Here, 3T, RH, then 500 Kelvin, 500 Kelvin and 9 bar. So many things are there. 9 bar pressure. You get this NO. This NO, you treat it with oxygen to form brown gas. NO when released, this oxygen will give you a brown color, that is due to the formation of NO. NO2 on reacting with water to form HNO3. NO2 to react with water to form HNO3 and the side product is NaNO. That NO is recycled. The products obtained, that is NO, is recycled to get again NO2. So this process continues. NO is recycled. What we get is only 68% nitric acid. To get 98% nitric acid, we have to dehydrate it with concentrated H2SO4. Remove all the water from that. We have to do dehydration with the dehydrating agent like concentrated H2SO4. Right, one question. NO becomes brown when released in air. Why? NO becomes brown when released in air. Why? NO becomes brown when released in air because NO reacts with oxygen of air to form NO2. NO2 is a brown gas. Properties of HNO3. HNO3 is a planar molecule. All atoms are lying on the plane. So all atoms are lying in a plane. Now here, this bond can resonate between these two. Double bond can resonate between these two. So due to resonance, you see more attraction. So write one question. NO bond in HNO3 is smaller than NOH bond. NO bond in HNO3 is smaller than NOH bond. Why? What happens? This is due to the resonance. That is OH. Here there is no resonance. This is something else. N O double bond O. So here it is minus, here it is plus, that's why it is new. So NO bond is resonating between this double bond is resonating between two NO bonds. So more attraction, but NOH bond, that is still. So that bond length is more than this NO bond. So answer is this is due to the resonance. Now HNO3, there is concentrated HNO3 and dilute HNO3. Concentrated HNO3 is a good strong oxidizing agent. It attacks metals except noble gases like gold and platinum. So with concentrated HNO3, when the metal reacts with concentrated HNO3, that salt will be formed. Salt will be formed, salt plus NO2 and water. First one, copper plus HNO3. Copper plus HNO3 is salt, that is copper nitrate plus NO2 and H2O. NO2 and H2O. Zinc plus HNO3 gives zinc nitrate plus again NO2 plus H2O. Here, this is by heart, but I by heart. Then 2NO2, 2N2, 2H2O, 2H2O, 2H2O. Next, with I2 plus HNO, that is HiO3 plus H2O, then carbon plus HNO. Carbon is oxidized to carbon dioxide. Iodine is oxidized to ionic acid. Gives next sulfur plus HNO3 acid. Sulfur plus HNO3 that we will do.